This video looks at one method for arriving at the form of the Kerr metric by first starting with a slow rotation in a weak field case. It goes on to use oblate spheroidal coordinates and to make use of various approximations, including the Schwarzschild case, to develop a suitable metric. The final form produced, known as a Kerr metric, satisfies the empty space field equations R subscript alpha beta equals 0. Right, so for a slowly rotating mass m in the weak field case, the space-time outside this mass can be described by this object here. And we saw that in the last video. And we also saw in the last video that when this 2gm on c squared r is less than 1, much less than 1, we have the weak field case, so that our metric can be further approximated by this object here. And we're here, just down here, J is defined as MAC, mass, angular speed, angular momentum per unit mass times the speed of light. Now let's continue the idea of approximation. And we have, starting with that last metric, that approximated metric, we have this object here. What we can now do is we're going to pull out this part here and just leave minus c squared dt squared. And we're just going to draw this bit here over here. And then we have this last term here, and then we're just going to add this bit on here. And we can do that. This is still approximately valid for to first order in A, the angular momentum per unit mass, to first order in A. That's still a valid approximation. All right, continuing down that line, we have this object here, and we can collect some terms and factorize out 2gm on c squared r outside of all of this. And when we do that here, we end up with this. We can express this bit here in brackets. We can factorize that as the square of these two terms here in the parentheses. Next bit. All right, this equation is still valid to first order in A. Now we know that rotating bodies bulge in the equatorial plane, that's away from the axis of rotation, and become oblate spheroidal in shape. Now in the case of our sun, its equatorial diameter is roughly 10 kilometers greater than its polar diameter. So there's a slight bulge at the waist, slight bulge in the equatorial plane, and the difference is about 10 kilometers. So very small. It's a weak field, slow rotating case. Now this suggests that we can use spheroidal coordinates or ellipsoidal coordinates as a starting point in our search for the form of the Kerr metric. So ellipsoidal or spheroidal coordinates are given by these objects here. Here's the descriptions for spherical polar coordinates, and we just know that to r we can add a small extension, a small quantity here. This a squared is added to r squared. All right, and to look at specific examples to give some idea of what that term did by in the x and y directions by just lengthening it a little bit. Well, in this case, we doubled it to exaggerate the effect here, but you can see how we go from spheroidal coordinates, the coordinates of a sphere in 3 dimensions, to oblate spheroidal coordinates over here. In the polar direction, the diameter is 20 units here. And for the sphere here in the x and y directions, the diameter is 20 units. However, in the spheroidal oblate spheroid, we have the diameter in the x and y directions as being 40 units. All right, and that's the addition of that a term in here. All right, so we have a bulging at the equator. All right, now we want to express the Minkowski metric in oblate spheroidal coordinates, and that metric is ds squared is minus c squared dt squared plus these differentials dx dy dz. And what we're going to do now is find the total differential. Dx is the partial of x with respect to r times the differential dr plus dx d theta plus dx d phi. This is for the spatial part, so it's this bit here we're going to fill out. We'll keep the time coordinates. When we do that, we get on the spatial part here, this bit here. Same in the dy direction, gives us this object here. You can stop the video and check all these calculations. In the dz direction, we get this, which is this object. And take the square of the differentials and add them together, and you will produce a big object like this. All right, now again, you can stop the video and check for yourself, but I use a software package to do this, but you can check that you end up with these. Next bit, if we then factorise the dr squared differentials and the d theta differentials and the d phi differentials. Now on the last page you can simply pull them out. You don't need a software package for that, but simply take them out and you end up with this. So here we are in the parentheses here, times dr squared, and then here d theta squared, and then all of this d phi squared. Let's have a look at the coefficient of the terms in the parentheses in front of the dr squared differential. And we have this object here, and if we just go collecting a little bit in the way of terms, if we have a look up here, you can see that you've got here, you can put a 2 up here and then a 2 out here, so we have a common denominator. And then here there's a trig identity we're going to make use of, so factor out the a squared here. Cos squared theta minus sine squared theta is 2 cos squared theta minus 1. When you put that in there, you'll come up with this object here. Next line down, we have these first two terms here, and then we separate this, we have these. Now if you notice here, this last term will cancel the first term, and then we're left with this term here and this one here. And when we divide through by 2, cancel out the 2's here, we have r squared plus a squared cos squared theta on top, and then we have underneath a squared plus r squared. That's this object here. We're actually going to name that and give that a symbol. But before we do that, let's have a look at d theta squared. Again, if you follow here, doing a whole lot of simplifying sign, you can stop the video and work through it, but it's not particularly something I need to go through now with this. But when you do that, you'll come down to this object here. Feel free to stop the video and calculate it for yourself. Next bit for the d phi squared coefficients. Again, this a little bit longer. A little bit of patience here, just be careful. You can fall into some dead ends if you're not careful, as I did along the way. But work your way through this and you'll come down to this object here. Again, stop the video and work it for yourself. All right, next minute, we can make the useful substitution that rho squared is r squared plus a squared cos squared theta, and that's what I mentioned earlier. Now coming back to the Minkowski flat space metric, let's substitute in what we have so far. Well, we have this dr squared plus this d theta squared plus this d phi squared, and we can then write that out like this. Again, we'll make that substitution. This bit here can be replaced with rho squared and makes the expression look nice and simple. So that's the Minkowski flat space metric in oblate spheroidal coordinates or ellipsoidal coordinates. Okay, but notice first thing, there is no cross term that we'd expect for a rotating source. So we need to have a look at that. What we're going to do is we can, by way of guesswork, we can add 2 terms to this. The 2 terms cancel out, so effectively we're adding 0 to the right hand side here, which means we're not changing it, but it will turn out to be useful. So let's do a little bit of guesswork here, go over, and when we do that, we're going to, let's collect the minus c squared dt squared at the front here, and make use of that in the form of something, this here, c squared dt squared, minus, this is the cross term we're adding here, and this bit here, we've seen this before earlier in the video. Then of course you have the second and third terms here, and then for the last one, we're going, because the cross term involves dt and d phi, it doesn't touch dr or d theta, so we're looking for something that involves dt and d phi, so that's going to affect the first term and the last term, and we can do that like this. Now, there'll be some sort of constant, something out here, some expression at the front here, and some coefficient out here that we need to find. We can work that out. These look here like a binomial expansion, something that we can square and expand out and get this, but what are these objects here? Well, something multiplied by this cross term here must then cancel out this thing multiplied by this cross term here. Okay, then we notice we've got 2a here, c dt d phi, c dt d phi. We have this object here, a squared plus r squared, and this object here, sine squared theta. All right, so what we could do then is we could multiply this term here by this a squared plus r squared over something, and we could multiply this term here by, this term here by a sine squared term over something. Okay, so we choose that to be here a squared plus r squared over rho squared, minus out front because we want this here c squared dt squared to be negative out the front here, so put a minus there. And then over here sine squared theta on rho squared, and when we multiply this by that, and this is multiplied by that, this becomes positive, minus and a minus. This becomes positive and a negative is negative, and so this term and this term cancels out. So effectively we've added 0 to the right hand side here, 0. So we haven't changed anything. One complication, we do have this a squared sine squared sine to the power of 4 term here, and we need this a squared plus r squared all squared d phi squared term here, and we'll see how we can work with that further on. Okay, so for the moment, these question marks have been found. We've got something that fits, at least in terms of cancelling out the cross terms. All right, so this gives us a line element in the form of this object here. So we now have cross terms suggestive of rotation, but we're also missing the presence of a source mass m in any of the terms. There's no mass m in here, and we found that rotation involves not just angular momentum or the speed of rotation, but it also involves the space-time. A line element to describe the space-time outside a rotating source must have something related to the speed of rotation, which we seem to have taken care of with the cross terms, but they must also have a mass term because it also depends on the mass, as we saw in the last video, and you need to watch that to know what I'm talking about there. And so we need somewhere to involve the mass term. Now we know that in the limit as A approaches 0, so as the angular momentum per unit mass goes to 0, as the source stops rotating, this line element we're trying to create, it must reduce down to that of the Schwarzschild case, or our metric for this space-time here must reduce down to the Schwarzschild metric. Now the Schwarzschild metric has the mass m of the source appearing in the dt, when I say metric, I mean the line element. It is interchangeably these days referred to as metric, but it is actually a line element. The line element should have dt squared, dr squared terms, as well as a cross term. Now we've got the cross term, but we want the mass appearing in front of the dt squared terms, the dr squared terms, and the cross term. Okay, so that suggests we need to alter the coefficients of the first and second terms, because you've got dt here and dr here. So we need, if we alter those, we should be, hopefully, let's see if we're on the right track. So let's do that. All right, let's have a look. So let's make this substitution, this minus a squared plus r squared on rho squared. We're just going to add a little bit on the end here, and we'll determine what form that takes. And then in the second term, that was over here, we had rho squared on a squared plus r squared on the previous page. We're going to add this a little element here. Why? The argument because it actually works out in the end, and you'll see why shortly as it comes through. So let's put those in. Here we go. And by the way, we've factorized collected terms. So we have c dt minus a sine squared theta d phi all squared. And then over here, a squared plus r squared d phi minus a c dt. Square of that, and it gives us what we had on the previous page with these in front, this bit up here and this bit here in front, plus we've added the k and the h here. Okay, so let's replace the rho squared with this term here. And we've got the h here. Rho squared here and here. All right, so put a few things back in. Let's go over. Now, in the case that the angular momentum per unit mass goes to 0, and that's the limit as a go to 0 of all of this. That's why I replaced the rho squared with this proper expression, this correct expression, rho squared. When a goes to 0, this line element must reduce down to that of the Schwarzschild case. Okay, so in the limit as a goes to 0, all these a's will go to 0. And when we do that, we're left with this object here, that object there. We've got an r squared here and an r squared down the bottom, so they will one will cancel out. This is all squared here, sorry, so that's r to the power of 4 all over r squared. When we do that, we get r squared sine squared theta d phi squared here, r squared d theta squared. And this was looking very, very familiar. Okay, and we'll just make it look even more obvious. Let's factorise our r squared here. When we do that, divide r squared by r squared, we get 1. The minus goes out front of the bracket in this case. K divided by r squared over here. We take the 1 outside, we factorise the 1, or factored the 1 out. Minus 1 out, sorry. So we've got a minus here as well. Now this is looking very familiar, like the Schwarzschild line element. Then we have this bit here. And then we have this bit here. Now all of this looks like the Schwarzschild line element. This is the angular part here. There's just, this looks close to the Schwarzschild case, and then this looks reasonably close, but we'll just go a little bit further next line down. So here we go here, and we're going to divide through by, or factor out r squared in the top line, leaving 1, factor out r squared out of here, leaving 1 plus h on r squared, this object here. And again, this is looking very familiar from the Schwarzschild line element, plus the angular part. Okay, so keep going. Now, that suggests that we make the following identifications, because as a goes to 0, in the limit as a approaches 0, this is equal to this, becomes a Schwarzschild metric element, G00. Okay, here we go. And so that implies that K is this object here, and in this case here for the H, we get this, that implies that H is just negative of this here. All right, so let's substitute that back in, what we've just found. So, okay, this is what we had before. We took the limit as a went to 0, and we now know what K and H is, so let's substitute that in. We get this object here. There we go, plus this bit here. Okay, so we substituted back in. So we now have mass, and we have the angular momentum, we have the cross term, we now have the mass. So we're getting somewhere now. We now make these helpful substitution. Rho squared again is this object here, and delta is a squared plus r squared minus this bit here. We'll call that delta. It just tidies things up, makes them easier to look at, understand what's going on. So coming back, here's what we had on the previous page. After we make our substitutions, we now have minus delta on rho squared times this bit here, plus this bit. So this line element is now highly suggestive of a rotating source. And we know that we have now the mass term involved, because through delta we have the mass term, delta and delta. We have the mass terms now. We have the cross terms. And so our line element is starting to take shape. So let's expand this and rewrite it. Here we go. Expand this out. That bit there. This bit here. All right. And then now let's just collect some terms here. And this bit here on the end goes up to the front there, so we end up with this. And then for the cross terms, we have this one and this one, and so that gives us this object here. And then we have these two terms here, and then finally this last one. Okay, so here's our line element now: c squared dt squared, c dt d phi, dr squared d theta squared, d phi squared. All right, now what we're going to do is make some substitutions so we can make the m mass term visible. A squared plus r squared minus delta is this object here, as we found before, and that equals just 2gm r on c squared. And we'll also introduce here sigma squared is this object here. Sigma squared is this object. All right, so writing all that out, beginning to look a little bit tidier now and a bit more like a line element where it can identify things. Look at the cross term here, these objects here, and we can write it in this form like this. This object here, notice the mass here, the cross term. All right, we know that there's a mass term in here where the dr squared is. And so this is one form of the Kerr metric we seek in Boyer-Lindquist coordinates. The Boyer-Lindquist coordinates are t, r, theta, and phi. And here it is. This is the line element. When I say Kerr metric, I do mean line element here, people. Sorry about that. It's just further on there will be the metric will explicitly appear. Now, to verify that it actually works, we need to check that it satisfies the Einstein equation in the vacuum or empty space case. All right, so here is our Kerr metric in this form. Remember, we saw earlier from the Boyer-Lindquist coordinates, so it takes this form here. So one form of the line element is this in Boyer-Lindquist coordinates, probably a very common form. Now we can make some further approximations to give us a more familiar form of the Kerr metric, or the one we're probably most familiar with textbooks. We go over here and we just look at this part here. We saw that in the front, and this in the rear, in front of d phi squared, and this one in front of c squared dt squared. Let's write these out explicitly. All right, write them out explicitly, substituting in. All right, now, and we then split these up into 3 parts, 1, 2, 3, and we notice here that a squared plus r squared, just if you ignore the cos squared term for the moment, as a rough approximation, that is 1. So I'll put a 1 there. And here we have 2gmr on this. This is our rho squared here. So if I put that back, I get the minus here, 2gmr on c squared rho. And you notice over here, this is r squared, a squared. This is a squared, but multiplied by a term that goes between 0 and 1. And so this on top is much smaller than this bottom line here, particularly as r grows large. And so we can take this as approximately 0. It's an approximation. So we end up with this object here. Now looking at the coefficient of the d phi squared term in the line element at the back there, writing this out explicitly, we get this 1 on rho squared times that object there. And the delta is this object in here. So writing that out, we get this. And multiply through by rho squared, which is this object here, and then splitting it 1, 2, 3 there. All right, and what we can say is there should actually be here a sine squared times all of this bit here. But what we actually get here is this is roughly r squared a squared divided by r squared a squared all squared. So that gives us a squared plus r squared. Roughly as an approximation. This is roughly of order, if we multiply that by sine squared, which I appreciate I've made an error, and I should have multiplied this by sine squared here. This, when I open the brackets, open the parentheses, I should have multiplied a squared plus r squared by sine squared theta, but that sine squared theta takes it between 0 and 1, and this is roughly of order 1, this object here, similar order to this because cos squared goes between 0 and 1. So that's roughly 1. There's a minus sign there. And then we have this bit here, 2gmr a squared sine squared all over c squared, and this is rho squared, and then times sine squared theta out the front there. All right, now roughly, again as an approximation, that's a squared plus r squared. We can ignore the 1 there in comparison to the other terms because it's very much smaller than the other terms, particularly these first 2 here. So we can ignore the 1 there as an approximation, and we end up with this object here, which is very much the first and last terms in the Kerr line element. Kerr space-time line element. And this leads to the Kerr line element. Double L there, unfortunately, I made a mistake there. And this gives us the line element in this form here. All right, and the Kerr metric can be expressed like this. Next step, just reminding ourselves once again, the line element is just this object here, and it's this version that satisfies the empty space field equations, subscript alpha beta equals 0, as I've checked using a software package to make sure. So this is the version to work with because it satisfies the empty space field equations by making them all go to 0. So when you solve R11, R22, and so on, you'll find that, and the R14 term, they all go to 0 individually, and so summed together they're 0. And that is it.